Now we want to see how to find out where the locus crosses the imaginary axis. So look at figure 17. I'll go to the previous figure, this figure. So these poles, we found a way to find the location and the angle of asymptotes. Okay, and I know this is the root locus. But the root locus at some point is going to cross the imaginary axis. So this point and this point. Now I want to find that point. I also want to find the gain that is corresponding for this movement. So why do I care about that? Well, on discussing stability of a system, when I crack up an unknown gain called K, and I'm trying to have the entire story in one picture. What I'm saying is that as I gradually increase gain, this pole comes here, this pole goes to infinity or negative infinity, and these two poles meet each other here, and then they go follow these lines. At a certain point here, this pole is going to be here, and this pole is going to be right on the j omega axis. This pole probably is somewhere in between here, and I don't know what happens to this pole. It's probably here. I don't know. So I'm going to have marginal stability. I want to find that gain that I get marginal stability. How would I find that? So how would I find where the locus crosses imaginary axis? Well, Routh-Horwitz. Do you remember Routh-Horwitz? That was what we used to do. So go back to section 33 and read what happens if an entire row of the Routh-Horwitz table is 0. As we studied, that means that we have symmetricity about the origin, which is what we want here. So what we need to do to find where the imaginary axis is being crossed is that we need to have Routh-Horwitz table, and we need to create the condition that causes an entire row of zeros. So for this system, the denominator is going to be, or if you try to write down the closed loop system, the characteristic equation is going to be 1 plus k times g times h, which is this. And then I'm going to get the characteristic equation is going to be this. If I expand it, I'm going to have s to the 4 10s cubed plus 32s squared plus 32 plus ks plus k. So I'm going to have 1 32k and then 10 32 plus k, and then I populate the table. I'm going to get this. When am I going to get an entire row of zeros? Well, this cannot be that line because it's going to have an entire row of zeros for k equals to 0. How about the next line? There wasn't enough space, so I'm showing this with a star. So the star is this. Okay, so I've done the math. So if I want to have, if I get k equals to 201.42, then I'm going to get this star equation equal to 0, which means that we have an entire row of zeros. And what that means is that we have two poles on the j omega axis, which means that we have marginal stability. You can verify this by plugging in k equals to 201.42 in the characteristic equation and checking the location of poles with MATLAB. The next topic is to find the breakaway points. Breakaway point is the point that the two poles on the real axis actually meet. So we previously studied that there's a difference between the point that two poles meet on the j omega axis and the location of asymptotes. These are not the same. So how do we determine the location of or the breakaway points? Well, this is the formula for it. dk to ds should be equals to 0. But what does that mean? K is a number. How can you take the derivative of that? Well, what it means is that if you have 1 plus kgh equals to 0, find k from it. How can you do that? So you move 1 to the other side, you get -1, and then you divide it by g times h, which we call it p here for simplicity. So bring 1 to the other side, divide it by gh. So 1 divided by gh, or sorry, -1 divided by gh, or -1 divided by p here. All this is saying is that take the derivative of that. Take the derivative of this with respect to s. So take the derivative of -1 divided by gh with respect to s and put that equal to 0. But it's important that after you solve this, it's going to give you a bunch of s that claims that those are going to be breakaway points. Notice that not all of them are correct. You have to check them and see which one makes sense. So for our example here, 1 plus gh is this. I find k by moving 1 to the other side, and I'm going to flip this. So I'm going to have -s times s plus 2 times s plus 4 squared divided by s plus 1. Take the derivative, put it equal to 0. I get s equals to -2.599. So -2.599 is actually the breakaway point. How do I check that? I go back to the figure. Is -2.999 make sense? Yeah. So I think it was -599. So -2.6. So this point is -2.6. Sometimes it might give us multiple values. It might give you -2.5 and +5. Obviously, +5 is not, like +3 or -1.5. Those are not correct numbers. You should check what you get. And yeah, so that's the correct answer. So let's see an example. Find the root locus of the system below. Well, so this is G, this is H. My open loop poles are 0 and 0 and -2. My open loop 0 is -4. Right? I can find the location, and I can find the, so first I put 0, 0, -2 and -4. So 0, 0, -2 and -4. On the real axis, the only segment that is in the locus is this, because there's 3 things on the right hand side of it. And as we know, locus comes out of the poles and goes inside zeros. Now we have 2 poles here that are located at the same location. Clearly, we are going to have asymptotes because they're going to meet each other right away. So, and the locus is going to leave the j omega axis. Sorry, leave the real axis. So we need to find the location and the angle of asymptotes. So for the location, I'm going to add up the poles. I'm going to have 0, 0, -2. And then I subtract from it my 0. So subtract from it -4. And then divide the number of poles, which is 3. Subtract from it number of zeros, which is 1. So 3 minus 1 is 2. So you're going to get 1 here. For the angle, you divide 180 degrees by the subtraction of number of zeros from number of poles. So 3 minus 1, which is 2. And you get times 2k plus 1. And you get 90 and 270 degrees.